Hello everyone, my name is Jaydev. I'm a PhD student in IIT Madras working with Professor Ramkrishna Pasumati. So, I will be doing this tutorial for week 2 in which we will be covering problems on the concepts that have been covered in the week, which include things on vector spaces, norms, matrix, then basis, span, then the fundamental subspace of matrix, and even the linear maps and linear transformations. So, we will do about 4 problems in this tutorial and I will be going through one by one. So, the first problem is we will try to prove the triangle inequality which was discussed while introducing the norms. So, it is said that, so we will try to prove it, we will stick to only 2 norm for proving this, but it can be proven for any other norm as well. So, I will say the triangle inequality is x plus y, norm of x plus y is less than or equals to norm of x plus norm of y. So, this is the triangle inequality and we will look at the proof. So, first we will square this right hand side and try to expand that. So, when we take the square of norm of x plus y, we get norm x square plus norm y square plus twice the dot product of x and y. Okay. At this point, we will introduce an inequality called Cauchy-Schwarz inequality. Which states that the dot product between two vectors x and y is less than or equal to norm of x times norm of y. Okay. So, and we will try to substitute this inequality into this above expression and see what we get. The square of norm of x plus y, I can now write it as less than or equals to norm x square plus norm y square plus twice norm of x and norm of y. So, now this is a simple, I can write it as a quadratic form. I can say norm of x plus norm of y whole squared. Now, if I take the square root on both sides, I will get, and assuming we are taking only the positive sign, norm of x plus y is less than or equals to norm x plus norm y. So, this proves the triangle inequality. So, now going to the second problem. Okay. So, this is the second problem. So, we are asked to show that a distance or a metric defined as square root of the absolute value between x and y, or the difference between x and y, is a metric on the real number space R. So, how can we show that this is a valid metric? So, we have seen that there exist 4 properties which every metric should satisfy, and the first among them is the distance between x and y should be greater than or equals to 0. The distance between x and y is equals to 0 if and only if x equals to y, and distance between x and y should be equal to distance between y and x. And finally, the triangle inequality, the distance between x and y should be less than or equal to distance between x and y summed with distance between y and z. Okay. So, for a metric to be valid, we said that these 4 properties should be satisfied. Now, we will see if this particularly defined distance satisfies all these properties and whether it can be called a metric or not. So, the first property, if you can see, okay, so let us say x, y and z exist in R. Okay. The first 3 properties can be actually very trivially verified, because if I take, I am assuming that, okay, so one assumption is assume only positive values for square roots. So, we are restricting ourselves only to the positive roots of this number. So, when we say that square root of absolute value of x minus y, absolute value of x minus y is always a positive number, the square root is definitely defined. So, we can say that the first property, that distance between x and y, which is equals to the square root of absolute value between the difference between x and y, is always greater than 0. And similarly, if x is equals to y, then I can say distance between x comma x, which is x minus x, is equals to 0. So, this satisfies the second property. Now, going to the third one, distance between x comma y is square root of absolute value of difference between x and y, which is also equals to the absolute value, square root of absolute value of difference between y and x. Because it is an absolute number, it does not matter whether it is y minus s or x minus y. So, I can write it as the distance between y minus x. So, now we have 1, 2 and 3 satisfied. Now, the fourth one is a bit tricky one. So, we will try to concentrate on that. So, what we will do is, we will again take, we will follow a very similar approach which we use to prove the triangle inequality. So, we take the square of the distance metric, and square is nothing but absolute value of x minus y, and this I can write it as x minus z plus z minus y, and which is always less than or equals to x minus z plus z minus y. Because just absolute numbers, you can always verify that this inequality holds. So, what we will do is, this number is greater than this. So, I can always add another term, a positive term to this, and this inequality will still hold. So, I will add this term. So, you can see that this is one square root, this is one square root, as we assume that we will consider only the positive values for the square root. 2 times of these 2 square roots will give us a positive number, and this whole thing on the right hand side will always be greater than or equals to this absolute value on the left. So, now I can say that, so now I can write it as square root of absolute value of x minus z plus absolute value of z minus y whole squared. So, I just converted this into a complete square, and now I can say that this is the distance between x and z, this is the distance between y and z whole squared. Sorry, this will be an inequality. So, finally, by taking the square roots, I will get d of x comma y is less than or equals to d of x comma z plus d of y comma z, which is my fourth property of the metric. Therefore, this shows that the distance metric, which was defined as the square root of the absolute value of the difference between two numbers x and y, is a metric on R. So, this completes the second problem. Now, we will go to the third problem. So, in the third problem, we are given a matrix A, which is a 3 by 4 sized matrix, which has elements as follows. Okay. So, we are given a 3 by 4 matrix A with the following elements. So, now we are asked to find its rank, nullity, a basis for the row space, and then the column space, and also the null space. Okay. So, we know that given a matrix, we can always find all these elements like the rank, nullity, a basis for the row space, column space, and the null space. So, during the lectures of this week, we have covered all these concepts. So, I will not be going into the definitions, I will be directly applying them to find it. So, during the lectures, it was said that the easiest way to find all these values or rank, nullity, and a basis is to find the row echelon form of any given matrix. Okay. So, now how do we convert this given matrix A into a row echelon form? Okay. So, if you recall the definition of the row echelon form, it says that the first or the leading entry of every row should be 1. So, I can check that all the leading entries. So, leading entry is the first non-zero element in a given row, and all of them are 1. So, it satisfies the first property. So, but if you go to the second property, the leading entry in a given row should be present in the column next to the leading entry of the previous row, which means, so if I take the leading entry in the second row, is now present in the first column. So, which is not right as per the definition of the row echelon form. It should be present in the second or higher columns, but not in the first column. So, what we have to do is we should make this value 0. So, how can we make this 0? So, we will do the following matrix operation. I will take R2 and replace it by R2 minus R1. R2 is nothing but the row 2 and R1 is row 1. So, what will I get? I will get something like this. Okay. So, now you can see that the leading entry in the second row is now present in the third column, which satisfies the property of the row echelon form. But now if you go to the third row, the leading entry is in the third column, but if as the leading entry in the second row is in the third column, the leading entry in the third row cannot be in the third column, it can be only in the fourth column or higher, or it need not be even present. So, we will do another operation as follows. We will take R 3 and subtract it from R 2 and replace it. So, this is what we get. Okay. So, now if we look at this matrix, it satisfies all the properties of a row echelon form. So, all the leading entries, so this is a leading entry, this is a leading entry. So, we call them as pivots. So, all the pivots are 1 and that satisfies the first property, and the pivots are present in the succeeding columns as the rows go on. So, that is also satisfied, and any 0 rows are always present at the bottommost thing. So, that is also being satisfied. So, now I can say that this is a row echelon form of given matrix A. So, now while defining the rank, we said that by looking at the row echelon form, the number of non-zero rows in the row echelon form will give me the rank of the matrix, because they are the only present independent rows in the row echelon form. So, if you look at this matrix A in the row echelon form, we have just 2 rows which are non-zero. So, I can say that my rank of A is equals to 2. So, which is nothing but the non-zero rows in the row echelon form. And then how about the nullity of A? For nullity of A, I can use the rank nullity theorem, which I can write it like this. Rank nullity of A is n minus the rank of A, where n is the number of columns of A. So, I can say it is 4 minus 2 and it is equal to 2. So, now I find out the rank and nullity. So, now how do we get a basis for the row space? So, the basis for the row space is very easy to find out from the row echelon form. It is just given by the span of the non-zero rows in the row echelon form. So, basis or I would not say even span, I will just say it is the bases are the non-zero rows in the row echelon form. So, this is given by, or I can say that the row space is the span of so this is my row space. Now, coming to the column space, we need to identify. So, we know that there are only 2 existing independent columns in this. So, we need to identify which of these 2 columns in the row echelon form are independent. We can clearly see that the first 2 are not independent. So, we can go with the first and the third. So, I will say that the column space of A is spanned by the vectors 1 0 0 and 2 1 0. Okay. So, now going to the null space. How do we find a basis for the null space? So, the definition of the null space says that um, all x such that Ax should be 0. So, if I take this A I want elements x 1, x 2, x 3, x 4 such that this product is equals to 0. So, I can find out two linearly independent vectors because I know that the nullity of A is 2. I can always find two linearly independent vectors which satisfy this equation, and so I will write down the null space of A is spanned by the vectors 0 0 2 minus 1 and 2 minus 1 0 0. You can always substitute these two in here and you will find out the product will be 0. And you can also verify that any linear combination of these two vectors which are the basis of the null space, if you find any linear combination of them and they substitute, and if they are substituted in this x, they will always result in 0. So, that is as per the null space definition. So, this brings us to the end of the third problem. Now, getting to the last problem of this tutorial. Okay. So, this is the fourth problem. So, we are saying there is a space V which contains all the real polynomials. So, which contains all the real polynomials, we mean the coefficients of the real polynomials of degree less than or equals to 3, and similarly there is another space W which also contains all real polynomials, but which are of degree 2 and less than 2. So, let D be a differential operator which obviously maps from V to W, and it can be easily verified that this D is a linear map. So, now given a basis for V which is 1 x, x square and x cube, and given a basis for W as 1 x and x square, we are asked to find a matrix representation for this linear map D, and we are also asked to find out the rank and nullity of this matrix. Okay. So, now firstly we can verify that V is a subset of R 4 and W is a subset of R 3. Which implies that D is a 3 by 4 matrix, or it has a 3 by 4 matrix representation, and we are asked to find out that matrix. So, first what we can do is we can apply this operator D over the given basis. So, I will say D of 1 is nothing but 0, D of x which is the differential of x which gives us 1, D of x square is 2x, and D of x cube is 3x square. Okay. So, these are nothing but the differentials of the given basis. So, now how can I write these numbers in terms of the basis for W? I can write it as follows: 0 times 1 plus 0 times x plus 0 times x square, which is obviously 0, and 1 times 1 plus 0 times x plus 0 times x square, which is equals to 1, 0 times 1 plus 2 times x plus 0 times x square, which will give me 2x, 0 times 1 plus 0 times x plus 3 times x square, which will give me 3x square. Now, I will put these as the columns of my matrix representation. So, the first column will be 0 0 0, these are the coefficients, and the second column will be 1 0 0, the third column will be 0 2 0, and the fourth column will be 0 0 3. So, given an element say y which belongs to V, if I apply this matrix over y, I will get an element which belongs to W, which is as per this particular basis. So, it is all as per this basis. So, before finding out the rank and nullity of this matrix, what if we say that we change the order of these bases? So, I will change just the order of one of these bases, let the basis for V remain to be the same. So, I will say that the basis for W is now changed to the following order: x square, x and 1. Okay. I just reverse the order. So, now what will be D? So, it is obvious that it cannot be the same. So, we just have to actually reverse these coefficients. So, we will get it this manner. So, as you see that depending on not just the basis, but even depending on the order of the basis, the matrix representation that you get for a linear map actually changes. So, this is to be very much noted and observed while dealing with linear maps and a given basis. So, now finally finding the rank and the nullity. So, the rank can be at most 3 because it is a 3 by 4 matrix, and you can actually observe that the rank is 3 because all the 3 rows are independent of each other. So, the rank of D is equals to 3, and if I apply the rank nullity theorem, I will get the nullity of D to be n minus 3, which is the number of columns, which is 4 in this case. 4 minus 3 is 1. Okay. So, this is how this problem is solved. I hope you got an idea of how the basis plays an important role in determining the matrix representation of a linear transformation. Okay. So, this brings us to the end of this tutorial. Thank you very much.